So in this video, we'll be talking about combinations. But let's start by remembering that in section 2.1 of your textbook, which is our Module 3, Lesson 1, we talked about the most basic concept in counting, the rule of products. In this section, we're going to investigate a different counting formula, but it's important to keep these fundamental processes in the back of our mind. So section 2.2, that's going to be our Module 3, Lesson 2. We saw that there's a special type of rule of products problem that occurs very often, and so we've given it its own name, and we call it a permutation. And we derived the formula for permutations. So in this section, we're going to derive a formula called combination, which is used to count subsets of a certain size. In many applications of the rule of products, the order is important. If the order is important, we call it a permutation. However, in some cases, the order is not important. If the order is not important, then we call it a combination. So for example, how many different ways are there to permute the 3 letters of the set A? This is what we learned in Lesson 2. We found that there were 24, and we had the formula. Permutations for objects taken 3 at a time is 4 factorial divided by 4 minus 3 factorial. It's 24. So that gives you 24 different orderings of 3 letters from A. But what if you were asked, how many ways can we select a set of 3 letters from A? We know that when we're talking about a set of 3 letters, the order doesn't matter. So by trial and error, we could find that we could have ABC, ABD, ACD, or BCD, and these are the only possible sets of 3 letters taken from ABCD. So order is not important. There are only 4 instead of 24 when order mattered. The notation for a combination, or for choosing 3 elements out of 4, is commonly this one here. So the parentheses where you have 4 on top of 3, but there's no dividing line like in a fraction. So make sure you note that. It's just the parentheses with 4 and then 3. Or you'll see the capital C parenthesis 4 comma 3 notation, which matches our permutation notation. And when we see either of these notations, we'll read that as 4 choose 3, or the number of combinations for 4 objects taken 3 at a time. Now we'll define the binomial coefficient. Let n and k be non-negative integers. Then the binomial coefficient, n choose k, represents the number of combinations of n objects taken k at a time. So one other name for the combination is the binomial coefficient, and there's a reason for that. Now let's investigate the relationship between what we already know about permutations and what we're learning about combinations to derive a formula for n choose k. So let's reconsider this 3 elements from a set of 4 elements problem. We said that there were 24 permutations, but only 4 combinations. So note that for each subset, like ABC, there are 3 factorial different orderings of the set, because we have 3 choices for the first spot, and 2 choices for the second spot, and 1 choice for the third spot. So in the right hand side of this table, you'll see listed all of the 24 different permutations. On the left side, you see the 4 different combinations. So in order to account for the 3 factorial different orderings, which we don't care about, we divide by 3 factorial. So the formula for 4 choose 3 becomes the number of permutations for objects taken 3 at a time divided by 3 factorial. but the number of permutations was already 4 factorial over 4 minus 3 factorial. This was the number of permutations. And so dividing by 3 factorial is just putting that 3 factorial now in the bottom. And so this would end up being 4 times 3 times 2 times 1 on the top, and on the bottom, 4 minus 3 factorial is 1 factorial, it's just 1. And then that's multiplied with 3 factorial, which is 3 times 2 times 1. So when we canceled, we'd just be left with 4 over 1, which is 4. And that's the answer we found. So this brings us to the formula that we're going to use for the binomial coefficient, or for combinations. And that is, if n and k are non-negative integers with 0 less than or equal to k less than or equal to n, then the number of k element subsets of an n element set is equal to n choose k, which will be given by the formula n factorial divided by n minus k factorial times k factorial. So here's the proof. There are k factorial many ways of ordering the elements of any k element set, which we saw above in the example about the 4 element set and the 3 elements taken from it. So n choose k is the number of permutations divided by k factorial, which is n factorial divided by n minus k factorial times k factorial. Otherwise, we could think of it this way. To construct a permutation of k objects from a set of n elements, we can first choose one of the subsets of the objects, and then choose one of the permutations of those objects. So by the rule of products, the number of permutations is, well, first we choose k elements from the set of n elements, and then we multiply by the number of possible permutations. Then if we solve this for n choose k, we get the formula from above. So here's an example. Assume that an evenly balanced coin is tossed 5 times. In how many ways can 3 heads be obtained? This is going to be a combination problem because the order in which the heads appear does not matter. We can think of this as a situation involving sets by considering the set of flips of the coin, 1 through 5, in which heads come up. The number of ways to get 3 heads will be 5 choose 3, which is going to end up being 5 times 4 divided by 2 times 1. If we do 5 factorial divided by 5 minus 3 factorial times 3 factorial. We have 5 times 4 times 3 times 2 times 1 divided by 2 times 1 times 3 times 2 times 1. So we can cancel 3 times 2 times 1, and we get 5 times 4 over 2 times 1, which ends up being 20 divided by 2, which is 10. Now, if we were taking order into account, then the 5 tosses could produce any one of the following mutually exclusive disjoint events. Either 5 heads, or 4 heads, or 3 heads, or 2 heads, or 1 head, or 0 heads. Then by the law of addition, since these are disjoint events, the total possibilities is 5 choose 5, which gives us how many ways could we have 5 heads? Well, there's just 1. 5 choose 4 is how many ways we could get 4 heads on 5 tosses, and there are 5. Then 5 choose 3, there are 10. 5 choose 2 is also 10. 5 choose 1 is also 5. 5 choose 0 is also 1. And when we add these up, we get 32. And of course, we know from our rule of products that because the coin is either heads or tails and we're doing 5 flips, it would be 2 to the 5 equals 32 ways But this is just one other way of seeing how the rule of products is connected to this idea. So it might seem like counting something two different ways, as we just did, is a waste of time. But when doing mathematics, it's often very instructive and leads to valuable insights. So in this case, it suggests a general formula for the sum. If we wanted to do the sum, k is from 0 to n, of n choose k, well, we've seen in the case of n equal to 5, we get 2 to the 5. A reasonable generalization might be that it's 2 to the n for general n. Let's talk about a couple of more examples and then we'll work through some exercises. A committee usually starts as an unstructured set of people selected from a larger membership. Therefore, a committee can be thought of as a combination. If a club of 25 members has a 5-member social committee, then there are 25 choose 5 different possible social committees. 25 choose 5 ends up being, this should be 25 times 24 times 23 times 22 times 21 divided by 5 factorial. So that ends up being 53,130 different ways that we could form the social committee by just randomly selecting 5 members of our 25-person group. If any structure or restriction is placed on the way that the committee can be formed, then the number of possible committees will probably change. For example, if the club has a rule that the treasurer of the club must be on the social committee, then the number of possibilities is reduced to, instead of 25 choose 5, will be 24 choose 4. Why? Well, because we've already chosen one. There's one treasurer. We just go ahead and say that person's automatically on the committee. So then we have 24 other people to choose from, and we need to choose 4 more people. So this ends up being 24 times 23 times 21 times, 22 divided by 4 factorial, which is 10,626. Otherwise, if the committee has 5 chairpersons other than the treasurer, or 5 including the treasurer, so 4 other chairpersons, and we require that a chairperson other than the treasurer be selected, then we'll have 24 choose 4 times 4. So the choice of 4 non-treasurers accounts for the 24 choose 4, while the need to choose a chairperson accounts for multiplying by 4. Then we get 42,504 different possible committees. So we have to be careful and just think each problem through and what it really means when we're doing the counting. By simply applying the definition of a binomial coefficient or combination as a number of subsets, we'll find out that there are n choose 0 equals to 1 way of choosing a combination of 0 elements. So if we just compute n choose 0 is n factorial divided by n minus 0 factorial divided by 0 factorial, and that's n factorial over n factorial times 1. So this is just just 1 rather. So there's one way of choosing a combination of 0 elements. Also, if we did n choose n, then we would find that this is n factorial over n minus n factorial over n factorial, which is n factorial over 0 factorial times n factorial, which is exactly the same thing that we already had. It's 1. So there's also one way of choosing n elements from a set of n. So this corresponds to, if we're thinking about the subsets of the set, the empty set and the set itself. So we could compute these using the formula as we have, but it's logical enough to just realize that there's only one way take the entire set from the entire set, or only one way to take an empty set from the entire set. Now let's see the exercises. The Judiciary Committee at a college is made up of 3 faculty members and 4 students. If 10 faculty members and 25 students have been nominated for the committee, how many judiciary committees could be formed at this point? Well, the problem tells us that we will definitely need 3 faculty and definitely need 4 students. So we can think of choosing the faculty and choosing the students as 2 different processes. So first we'll choose faculty. We need to choose 3 faculty. And how many do we have to choose from? We have 10 to choose from. So this will be 10 choose 3. And then I'll choose the students. Because it's 2 processes back to back, that's going to be multiplication. So I need to choose 4 students, and how many do I need to choose from? I have 25 to choose from. So I could write this out. This would be 10 factorial divided by 7 factorial times 3 factorial. And that would be multiplied by 25 factorial divided by 21 factorial times 4 factorial. And we're definitely going to see some cancellation here, but even with the cancellation, this computation is quite large, not really able to be done by hand. So for these calculations, you can certainly use a calculator of your choice. This is going to end up being 1,518,000 different judiciary committees that we could choose. But even if you are using a calculator, you absolutely must know these formulas for permutations and combinations. And we will have examples, there will be situations where it's much faster to just do the cancellation. Alrighty. Next, suppose that a single character is stored in a computer using 8 bits. How many bit patterns have exactly 3 ones? So this will be equivalent to, and the hint here says, think of a set of positions that contain a 1 to turn this into a question about sets. So this will be 8 choose 3. 8 choose 3 is the number of bit patterns that have exactly 3 ones. And this will be 8 factorial divided by 3 factorial times 5 factorial. Now that's, on top we know 8 times 7 times 6 and so on till we get to 3, 2, 1. And here we have 3 times 2 times 1 times 5, 4, 3, 2, and 1. So if I do my cancellations, these are going to cancel. So then what I'll be left with is 8 times 7 times 6 divided by 3 times 2, which is 6. So this also cancels. So this is 56. So for part A, there are 56 bit patterns that have exactly 3 ones. Now for part B, how many bit patterns have exactly, or have at least 2 2s? So one way of thinking about this would be to say this is those bit patterns that have 2 2s plus how many have 3 2s plus how many bit patterns, 3 1s plus how many bit patterns have 4 1s, and so on, all the way up to how many have 8 1s. That's one way of thinking of it because it's at least 2. Maybe a simpler way of thinking of it would be to say, well, let's take the total number of bit patterns, which should be 2 to the power 8, because I have either 0 or 1, that's where the 2 comes from, and since it's 8 bits, that's why I have 2 to the power 8. 2 to the power 8, and then just subtract just 8 choose 1, those that have 1 1. And I'm also going to subtract those that have no ones. So that's just probably a quicker way. And this is going to be, well, 2 to the power 8 is 256. I know that there's one way to choose 0, and there are 8 ways to choose 1. So this is -8 minus 1. And so you end up with exactly 247 bit patterns have at least 2 ones. Now, how many subsets of the set 1, 2, 3, ... 10 contain at least 7 elements? So, similar to the last problem, at least 7, that's going to be 10 choose 7, that's how many of them have exactly 7, plus 10 choose 8 is how many of them have exactly 8, plus 10 choose 9, that's how many have exactly 9, plus 10 choose 10. And if I computed these, this is 10 factorial over 7 factorial times 3 factorial, plus 10 factorial over 8 factorial times 2 factorial, plus 10 factorial over 9 factorial times 1 factorial, plus 10 factorial over 10 factorial times 0 factorial, which is 10 times 9 times 8 divided by 6, plus 10 times 9 divided by 2, plus 10 divided by 1, plus 10 divided by 10. So this ends up being 120 plus 45 plus 10 plus 1, which is 176. Next, a poker game is played with 52 cards. How many hands of 5 cards are possible? So this is simply 52 choose 5. So the number of ways of choosing 5 cards from a 52 card deck. And this ends up being 2,598,960. If there are 4 people playing, how many 5-card hands are possible on the first deal? So the first player will get 5 cards, and there are 52 choose 5 ways that the first player can get 5 cards. Then there'll be 47 choose 5 for the second player, 42 choose 5 for the third player, and 37 choose 5 for the fourth player. So we can think about these as successive processes, even though when dealing cards we don't usually deal 5 to the first person and 5 to the second person in that way. We can still think of them as successive processes. Once the first person has 5 cards, then there are only 47 more cards to be chosen from for the second person. And as you can imagine, this should be a really huge number because we already had 2 million and something here, and then we're multiplying it by other very large numbers. So I didn't actually compute this, but it should be a very, very large number. A flush in 5-card poker is 5 cards of the same suit. How many spade flushes are possible in a 52-card deck? I'm going to let this be A. And how many flushes are possible in any suit? So for A, how many spade flushes? Well, first it helps to know that the deck has 52 cards and there are 4 suits. So 52 divided by 4 suits is 13 cards per suit. So I have 13 spades. Since there are 13 spades, a flush of spades can be dealt in 13 choose 5 many ways, and that ends up being 1,287. Then the next question is how many flushes are possible in any suit? As we said, there are 4 suits, so I'm going to say this is 4 times 13 choose 5, or 4 times 1,287, or 5,148 possible flushes, if it doesn't matter what suit. In poker, a full house is 3 of a kind and a pair in one hand. For example, 3 fives and 2 queens. So how many full houses are possible from a 52 card deck? So our hand is going to be 5 cards. 1, 2, 3, 4, 5. And all we know is that 3 of them are going to be 1 card. And the cards are Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, King, and Queen. So there are 13 possible cards. Or in other words, there is the deck of 52 cards divided by the 4 suits, so 13 in each suit. So 13 different types of cards, and I know that the first 3 cards will be one, and the next 2 will be another kind. And since there are only 4 of each card, so for example, the 5 card, there are only 4 fives, I can't have a total of 5 of the same thing. So first I could think of this as choosing which cards are going to be my 3 of a kind. So I have 13 different choices of cards. I'm just going to choose one of them and say that I have 3 of a kind. But then the question would be, which suits do I have? I could have the 5 of spades with the 5 of hearts with the 5 of clubs, or I could have the 5 of hearts with the 5 of diamonds with the 5 of clubs. So that will be 4 choose 3 in order to know which suits. So this is how many different 3 of a kinds I could have. But then I'm also going to have a pair. I have 12 cards left over because I've already chosen one of the cards to be my 3 of a kind. So I'm going to choose 1 from 12. And then again, the suits matter, so I'm going to choose 2 suits from the 4 possible suits. So this is going to be the number of full houses possible. So this ends up being 13 factorial over 12 factorial times 1 factorial times 4 factorial over 3 factorial times 1 factorial times 12 factorial over 11 factorial times 1 factorial times 4 factorial over 2 factorial times 2 factorial. Well, 13 factorial divided by 12 factorial is just 13. 4 factorial divided by 3 factorial is just 4. 12 factorial divided by 11 factorial is 12. And then for the last one, 4 factorial is 24. Divided by 2 is 12. Divided by 2 again is 6. So 13 times 4 times 12 times 6 is the number of full houses. And that ends up being, I think, 3744. And that is the final example in this lesson on combinations. So we'll have one more lesson in our module on counting, and then we'll move on to the next module.